Welcome to today's episode. We're diving into the intricate world of SQL transaction isolation levels and the anomalies that can arise from them. If you work with databases, understanding these concepts is essential because they play a crucial role in maintaining data integrity and performance. We'll explore the different types of read and write anomalies, the various isolation levels available, and the mechanisms that help manage concurrency in database systems. Let's kick things off by looking at read anomalies. These can significantly impact the accuracy of the data retrieved during transactions. There are three main types to be aware of. First up, we have dirty reads. This happens when a transaction reads uncommitted changes made by another transaction. It can lead to inconsistencies since the data being read might never actually be finalized. Next, we encounter non-repeatable reads. Imagine a transaction retrieving the same row multiple times but getting different results each time. This occurs when another transaction modifies the row between those reads, creating uncertainty about what the data truly represents. Finally, we have phantom reads. This is when a transaction queries a range of records and sees different results because another transaction has inserted or deleted records within that range. This can create confusion, especially for applications that depend on consistent datasets. Now, let's shift our focus to write anomalies. These can introduce several issues during transaction processing. One common problem is lost updates. This occurs when two transactions read the same data and then both try to update it. The last update might overwrite the changes made by the first transaction, resulting in data loss. Then there are dirty writes, which happen when a transaction writes to a row that has uncommitted changes from another transaction. This can potentially corrupt the data. Lastly, we have write skew, which emerges when two transactions read the same data and make changes based on that data, leading to inconsistent outcomes. To address these anomalies, SQL provides various transaction isolation levels, each with its own trade-offs. The first level is read uncommitted, which is the weakest isolation level. It allows dirty reads, offering the highest performance but at the cost of data integrity. Next is read committed, which prevents dirty reads, yet still allows for non-repeatable and phantom reads. It strikes a balance between performance and consistency. The repeatable read level disallows non-repeatable reads, ensuring that if a transaction reads a row, it will see the same data throughout its execution, although phantom reads can still occur. Finally, we have serializable, the strongest isolation level. It ensures that transactions appear to execute in a strict sequence, which enhances consistency but requires significant coordination and can lead to performance bottlenecks. In addition to these traditional isolation levels, there are alternative methods for handling transaction management. One such method is snapshot isolation. This approach allows transactions to work with a static view of the data, reducing the chances of lost updates. However, it can introduce write skew, since transactions may not be aware of changes made by others. Another alternative is optimistic concurrency control, which operates on the assumption that conflicts are rare. Transactions proceed without locking resources and are validated before committing. If a conflict arises, the transaction is aborted and can be retried. Then there's multi-version concurrency control, or MVCC, which enhances performance by allowing multiple versions of records to coexist. This reduces contention and improves read performance, as readers can access the version of the data that was available at the start of their transaction. On the other hand, pessimistic concurrency control proactively manages conflicts through locking mechanisms, ensuring that transactions don't interfere with each other. While effective, this approach can lead to contention and scalability challenges. Let's also touch on timestamp-based controls, which play a vital role in transaction management. Each transaction is assigned a timestamp that dictates its validity concerning concurrent operations. If a read operation tries to access a value that has been updated by a more recent transaction, it gets aborted to maintain the order of operations. This principle, known as the write rule, helps manage outdated data effectively. When transactions are aborted, they restart with new timestamps to prevent repeated failures, ensuring that the database remains consistent and that transactions can proceed without being hindered by outdated information. We can't forget about lock-based concurrency control, a widely used approach for managing access to database objects. This method employs explicit locks to prevent conflicts between transactions. The two-phase locking technique is particularly common, where transactions acquire locks before accessing data and release them afterward. While this method is effective, it can lead to issues like contention, where multiple transactions compete for the same locks, and scalability challenges, especially in high concurrency environments. Understanding these dynamics is crucial for database administrators and developers alike. In summary, navigating SQL transaction isolation levels and the associated anomalies is essential for maintaining data integrity and optimizing database performance. By grasping the different types of read and write anomalies, the various isolation levels, and the concurrency control mechanisms available, professionals can make informed decisions that enhance the reliability and efficiency of their database systems. As we continue to explore the complexities of database management, these concepts will remain foundational in ensuring our data remains accurate and consistent in an increasingly interconnected world. Thank you for joining us today. We look forward to our next episode, where we'll delve deeper into the world of database optimization strategies.